So we're continuing on derivatives as a rate of change. In here, we had talked about yesterday the following definitions. And so let's just read through and recall. And so recall that if we have some function s equals f of t, s represents the position of some object, the displacement of the object over time interval from t to t plus the change of t. So if we're looking for the displacement of this object, all we're going to do, we'll look at the change of s, which is equal to f of t plus the change of t minus f of t. So if we were finding the average velocity of the object over time, and we can denote that with v with a little subscript av, we would look at the displacement of our object. How far did it travel? And then the travel time. And displacement, actually, we could have been going forward and then coming back. And so the displacement would be that interval. How far from the beginning? Okay, so but the instantaneous rate of change or instantaneous velocity, which we stopped calling it instantaneous, but when we say velocity without that average in front, that's where we're looking at that change in time being so infinitesimally small, making that go to zero. We're looking at the limit of the change of t going to zero of our difference quotient, which we had talked about before is just the derivative of, in this case, s with respect to t, and is our velocity function. So knowing that, I just wanted to review and do one quick problem that was similar to what we had done yesterday. I'm not going to go through all of it, but I just wanted to do, because I want to save some time and go through some other types of problems. But I want to go through part of this. And so in here we have our position function. In this case, we have 25 over t squared minus 5 over t. We're given that the time interval that we're looking at is between 1 and 5 seconds. I'm assuming these are seconds. And we were talking about position being meters. So part A says find the body's displacement and the average velocity for the given time interval. And so find the body's displacement. We want to figure out what the position was at time 1, and we want to find out what the position was at time t equals 5. And then we want to see what was that distance. And so if we look at s of 0, not 0, 1, starting at 1, and plug in 1 wherever we see a t, we would get 25 all over 1 squared minus 5 all over 1. And so if we simplify that, we get 25 over 1 minus 5 over 1. So we get 25 minus 5, which is 20. And then if we look at time at 5 seconds, this is equal to 25 all over 5 squared minus 5 all over 5. Well, 25 over 5 squared, that gives us back 1 minus 5 divided by 5, which is 1. So 1 minus 1 is 0. And so if we look at the displacement, we've gone 20 meters. But if I look at it as from the ending position minus the starting position, this is going to give us back negative 20. So we were moving backwards, but let me just check on something first. We have the negative 20 meters is the displacement. So that was just part A, was finding the body's displacement. Now finding the average velocity. So that's we're looking at the displacement over the time period. And so the average velocity is the negative 20 meters all over the time interval. Well, we had 5 seconds to 1 second. So that is 4-second time interval. And so this is going to be negative 5 meters per second. So remember velocity, that didn't give us the speed. Well, it gave us the speed, but it gave us the direction. If this had asked me for the speed, I would look at the absolute value of that, and that would be 5 meters per second. But velocity is also telling me direction. In the negative, I'm going in the opposite direction. So for the other questions, I'm not going to go through with it. I'll just discuss them really quickly, but I'm not going to solve them mathematically. Part B says find the body's speed. So recall, to find the speed is equal to the absolute value of our velocity function. So recall, to get velocity, we would just take the derivative of our position function, and we would take the absolute value to get the speed. So acceleration, and you wanted to find this, it asked us to find the body's speed at the endpoints. And so in this problem, we would look at our velocity at our endpoint. So we want to find the velocity at 1, or speed, so absolute value of that, and the velocity at 5 seconds, the absolute value of that for speed. Acceleration, recall, acceleration we found by taking the derivative of our velocity function. And so our acceleration function, and we denoted that by a sub t, this was equal to the derivative of velocity, which is equal to the derivative of our, so double derivative of our position function. And again, it wanted to find, in that part B, wanted us to find it at the endpoint. So a sub 1 and a sub 5. That last question, part C, it says, when, if ever, during the interval does the body change direction? And so we could tell if it's changing direction based off of the velocity. If it's going forward, we know that the velocity is greater than 0. If it's going backwards, we know the velocity is less than 0. And so we want to find when it's equal to 0 and test sides to see if our signs are changing. Is it going to be opposite signs when we look at values on each side of where it's equal to 0? And if so, then it's changed direction. If we've gone from positive velocity to negative velocity, that's changed, or negative velocity to positive, that's also changed. So I
have a question. Going back to the first part where you found the average velocity, where'd you get the 4 from?
The 4, because the average velocity, by looking at this, I'm looking at our change in S, which we had found to be that negative 20 over the change in time. And so in our time, we had 5 seconds minus the 1 second. And so that would have been just 4 seconds that we were looking at. So average velocity is displacement over the time period. And so that's where the 4 comes from.
Okay, thank you.
Yeah. Any other questions on that? Okay, so I normally don't do this, but I am today. I am going to try to show you a video. So I was doing some research on lecturing for today, and I saw this video, and I think that it does a great representation of what's going on with the physics here with velocity and acceleration and position of an object. So I'm going to play this video. I'm not going to record it while I'm playing it. So for my students in my class, I'll have the link and you can watch it later. I do have what it is here. So those people who, maybe it doesn't say who it is. You could always look this up on YouTube and find it. So I'm going to pause the recording for now, and then we're going to discuss what we had just learned and apply it to a problem. Okay, so unfortunately I showed the wrong video, so it doesn't matter. And unfortunately I did not start up the recording when I was explaining what I had learned yesterday from the video I wanted to show you. Long story, very short, is it had to do with a football player and a football player moving forward once he's gotten the ball, and velocity being greater than 0, he's moving away from his initial position, and the acceleration being greater than 0 if he is starting to run towards that goal line. If he was being tackled and he was held onto, maybe they grabbed his shirt, he would still be moving forward, but the acceleration is going to be decreasing, so it's less than 0. If for some reason he's stopped, the person tackling the person with the football stopped and stopped the guy from running, and he started to pull him backwards, we know the velocity is negative. And he might be pulling them back at a faster rate, and that acceleration is going to be negative too. So looking at that, or knowing that kind of information about position and velocity and acceleration, let's look at the following example. So we have a figure in front of us. We need to notice that the figure that they're giving us is actually the velocity function. And so this is the function that we would have graphed if we took the derivative of our position function.
I can't see the figure that you're talking about. I still see the video.
Thank you guys. Thank you. So let me just change my screen really quickly. Now you should be able to see this figure in front of you. And again, this is our velocity function. And so this is giving us the slope of our position function. And it's given us that our position function was meters per second. Or this is our velocity function is meters per second of a body moving along a coordinate line. Okay, so let's just talk about this a little bit, and then we'll kind of answer the questions that it's asking. But if we look at this function in here, this is our velocity function. And so remember, velocity, it's going to be greater than 0 when we're moving forward. That's not going to work. So I can tell that the object is moving forward from the interval from 0 to 2. And it also looks like it's above the x-axis, right, at 7. And so it's above the x-axis from 7 seconds to 10 seconds. Notice that when it's equal to 0, that is, sorry, a max or a min. We're talking about, if we look at the original function, right? This is again is talking about our derivative. And if you look at our original function, our slope is going to give us 0 at a max or a min. And so I can see that it's moving backwards when it's below the x-axis. In here, we can look at where it's changing direction. So when does a body reverse the direction is our first question. So we talked about that it was reversing directions when the velocity, earlier in the video, when the velocity changed signs. And so notice that our velocity is changing signs at 2 seconds. It's changing signs also at 7 seconds. Okay, so the other thing it's asked us, when approximately is the body moving at a constant speed? Well, if it's moving at a constant speed, that's telling me that the slope is the same. If the slope is the same, and this is the picture of this is the derivative function of my position function, the slope is remaining the same here when x equals 3 to x equals 6, not x, that's t. So it looks to me that it's moving at a constant rate between 3 and 6 seconds. If it's asking me to graph the speed, well, the speed, remember, is the absolute value of the function. So only difference would be that this piece underneath the x-axis, this piece in here, I have to reflect this across my x-axis. And so notice that if I reflect this across my x-axis at between 3 and 6, that's going to be a horizontal line at 3. And so we would get this piece in here. So the graph of the speed wouldn't have anything below the x-axis. It would just be this piece. And the last question asks us to graph the acceleration, where to find. Well, if we're graphing the acceleration function, we need to find out what the slope is of our velocity function. So I'm just going to erase this for now so I can see better. So it shouldn't be too bad because this doesn't have any curves. And so we have lines in here and it's easy to find the slope of lines. So if I'm looking at the interval from 0 to 1, notice I can think about this as rise over run. I'm rising 3 and I'm running over 1. And so I know that my slope for this first piece is 3. So between 0 and 1, I have a horizontal line at 3. Okay. Recall that the derivative doesn't exist when we have sharp turns. And so we're going to put an open circle here at this sharp corner at t=1 horizontal line. So now let's look at the next piece of our graph. That next piece of the graph, that's a line, right? It's decreasing. And I can figure out, and this is decreasing from t=1 to t=3. And if I think of this as rise over run, well, I'm falling 6 and I'm running over 2. So if I'm falling 6, running over 2 in the positive direction, that would be -3. And so my slope for this piece I know is -3. And so again, I have this horizontal line at -3. This time just -3, not positive. And so I'm going to start at 1. Open circle, and I'm going to stop at 3.
The screen share, I think it's frozen.
Of course, let's see. We're going to get fast at this. Let's see on 2 seconds. So we're drawing that vertical line between 0, t=0 and 3, not vertical, horizontal, at -3. If we look at the next piece of our velocity function, notice this is a horizontal line. My slope is 0 there. And so if my slope is 0 there, then I know that I'm going to have a horizontal line at my x-axis between these values of 3 to 6. Open circle because it's a sharp corner. Okay. From 6 to 8, we have an increasing function. So my acceleration is going to be positive. And again, we can look at the slope. I'm rising up 6. And I'm running over from 6 to 8 too. So my slope here is 3. And so I have from 6 to 8 a horizontal line. Another sharp corner, so the derivative doesn't exist. And then I'm decreasing. So I'm decreasing at a rate of from 8 to 10. I'm falling 3 and running over 2. So that is going to be 3/2. Okay. So just estimate 1.5.
Wouldn't it be -1.5 since it's
Oh,
decreasing?
thank you. Falling -1.5. Okay, so we just
I had a
graphed our
question.
slope.
So for the slope that's 0, why would it be from 4 to 6?
Slope at what?
The slope that's 0 on the second graph, you put it from 4 to 6. Why is that?
Okay, and maybe I got that off a little bit too. So that should have been at 3, right? because this is 3 here. So it should be this here at 0 should be from 3, starting at 3 to 6. So I need to extend this a little bit. Yeah, I knew that was going to happen. Let's see. So open circle, solid. There we go. Anything else that you guys see? Thank you for catching that. You guys are awesome. Okay, so economics, business, a lot of times use rates of change. And rates of change now we know are derivatives. And so let's look at an application problem. But before we do that, I want to look at some terminology so that you're aware of this. So economics, or economists, sorry, have a specialized vocabulary for rates of change and derivatives. So instead of calling the rate of change or derivative, they call them marginal. So in a manufacturing operation, the cost of production, C of X, is the function of X, the number of units being produced. So if we have some cost function, C of X, if they say the marginal cost of a function, this is the rate of change of the cost with respect to the level of production. And so to find that, we're going to look at d of c over d of x, or the derivative of our cost function with respect to x is another way to state that. If it's talking about marginal revenue, then we're looking at the rate of change of the revenue with respect to the number that we've produced. And if we're talking about marginal profit, we're looking at the rate of change of our profit depending on the number of units produced and sold. Okay, so knowing that, let's look at a problem and solve it. And so in front of us, we have an example that says, so suppose that the dollar cost of producing X washing machines is given to us by C of X equals 2,000 plus 100X minus 0.1x squared. So first question asks us to find the average cost per machine of producing the first 100 washing machines. Okay, so in here, because it says the word average, that's what I'm looking at, the change in my cost function. So I want to look at what is C of 100. And so if I look at C of 100, notice that I'm going to go back in here and plug in 100 wherever I see an X. So I have 2,000 plus 100, all times X, so all times 100, minus 0.1, all times 100, quantity squared. Okay, so I have 2,000 plus 100 times 100, 4 zeros. So that's going to give me 10,000 minus 0.1 times 100 times 100. So times 10,000. So I have 2,000 plus 10,000 minus, we'll move my decimal, I'm multiplying by 0.1, so move my decimal over 1, so that would give me 1,000. So that's 12,000 minus 1,000, so that is giving me 11,000. So that's the cost of the first 100. but we want the average cost. A minute. So we're looking here, the average cost. So the cost of 100 units or the first 100 washing machines. We're going to look at this, but divide it by 100. So C of 100 divided by the 100 machines. And so C of 100 that we found was 11,000 divided by 100. This is going to give me $110. So that's the average cost of producing each machine, 100 machines each. So when it says find the marginal cost, that's telling me I want to find the derivative of my cost function when I have 100 washing machines. So we want to find the derivative of this cost function. And now we can, since we have the tools, we can use the shortcut and use the general power rule. So when we're taking the derivative of a constant 2000, that's 0. Taking the derivative of 100x gives us back 100 minus the derivative of 0.1x squared. So bringing down our power, we get negative 0.2. Subtract 1 from our exponent, we get x. So evaluating this at 100, then as we get back 100 minus 0.2 times 100. So 100 minus, let's gonna move it over once. So this is gonna be 20. So this is equal to 80. So the marginal cost when 100 washing machines are produced is $80. The last piece says show the marginal cost of the 100 washing machines are produced as approximately the cost of producing one more machine after the first 100 have been made, and calculating the latter cost directly. And so what this is telling me is I want to look at what is C of 101 minus C of 100. We already got C of 100, but let's just quickly, because time is almost done. Let's go in and find C of 101, plugging in 101 wherever I see an X there. So I have 2000 plus 100 times 101 minus 0.1 times 101 is squared. If we do this, we get, this is equal to $11,079.90. And so if we look at that difference, this $11,079.90 minus C of 100, which was 11,000, notice that that difference is $79.90. And so that cost of producing that 101st washing machine was $79.90, which is almost identical to the marginal cost of 100. And so we can, it's easier to find the derivative and finding the value of X before the one you want to see. So basically C prime of X is equal to the same thing as producing the X plus 1 item. We're only off by 10 cents in here, where this was a lot faster to do than having to go back and plug these in wherever we see an X and then take the difference. So this is all of 3.4 in our textbook, the rate of change, looking at it as the derivative and looking at some applications.